I'm introducing Isomap, a technique we use to simplify complex datasets by reducing the number of dimensions while trying to preserve important relationships between data points. Think of it like creating a detailed map from a satellite image. You capture the essential features without all the extra, overwhelming detail. This is a multiple-choice question about the characteristics of the Isomap algorithm, focusing on its strengths and weaknesses. I'll guide you through assessing each statement, and it is a great way to test your understanding. We're diving into a problem that's common in data science. High-dimensional data is messy, it's hard to visualize and work with. Isomap, from the Sklearn library, helps make it easier to understand. The quiz will test your knowledge of its properties. Let's talk about the Isomap algorithm. It's a clever method for dimensionality reduction. It tackles high-dimensional data by focusing on the distances between data points, cleverly arranging them to preserve the overall shape and relationships even after reducing the dimensionality. We begin with high-dimensional data, that is, lots of features to consider for every data point. Imagine each data point like a detailed description of a person, with measurements for height, weight, age, income, etc. We aim to reduce that number of features so we can focus on essential relationships without sacrificing information. Here, we're talking about how long Isomap takes to run. The time scales roughly with the square of the number of data points. If you double the data, it'll roughly take 4 times longer to compute. This makes the algorithm computationally intensive for large datasets. Isomap excels at keeping the distances between faraway points accurate, even after dimensionality reduction. Think of it like creating a map. It aims for accurate representation of the overall landscape, even if some minor details might be slightly off. This statement is false. Isomap doesn't use simple linear transformations. It's a nonlinear method, capable of capturing more complex relationships in the data that linear methods miss. Before Isomap starts reducing dimensions, it creates a graph connecting nearby data points. This graph represents the local structure of your data. This step is essential in capturing the relationships before we start simplifying things. This instruction tells you that you might need to select more than one answer choice. It's a multiple-choice question where multiple options could be correct. Pay close attention to each statement. This is the main question. You need to evaluate each statement and determine if it accurately describes Isomap, a dimensionality reduction technique. Let's find those true statements. This statement is incorrect. Isomap is actually a nonlinear technique. It deals with complex curves and shapes in data, not just straight lines like linear methods. This statement is true. Isomap's main goal is to keep the large-scale distances in the data intact during the dimensionality reduction process. Think of it like keeping the overall shape of a map consistent, even if some small details are lost. This is approximately true. The time Isomap takes to run increases roughly with the square of the number of data points, n squared. It's not exactly quadratic, but close enough for a multiple-choice question. Imagine how much longer it takes to sort a list of 100 names versus 10. This is true. You must set a parameter that tells Isomap how to determine which points are considered close to each other when creating its internal neighborhood graph. Think of setting the radius around each data point to determine its neighbors. I see this as a heading introducing the core topic, Isomap, an algorithm used for dimensionality reduction. It's a nonlinear technique, meaning it handles data that doesn't follow a simple straight-line pattern. The algorithm focuses on preserving the overall structure and relationships of the data. We'll explore how Isomap works in detail. This is simply a multiple-choice question about Isomap algorithm. I understand you're about to be quizzed on its properties and behavior. Isomap starts by taking a dataset as input. This dataset has many dimensions or features. Think of a dataset describing images, where each dimension could be a pixel's color intensity. The challenge is reducing the dimensions without losing essential information. We need to make this data more manageable for analysis. After creating a neighborhood graph, we need to calculate the distances between all data points. Instead of directly using the Euclidean distance, straight line distance in high dimensions, Isomap uses geodesic distances. Imagine the Earth. The geodesic distance between two cities is the shortest distance along the curved surface, not a straight tunnel through the Earth. Floyd-Warshall algorithm is used to compute these geodesic distances efficiently, though it's computationally expensive. Multidimensional scaling, MDS, is a technique that uses the geodesic distance matrix, computed in the previous step, to embed the data points in a lower dimensional space. It arranges the points such that their distances in the low-dimensional space closely match the geodesic distances in the original high-dimensional space. This is the core dimensionality reduction part of Isomap. I think of this as carefully arranging points on a map to reflect their actual distances. The final result is a low-dimensional representation of the original high-dimensional dataset, preserving the global structure and relationships between the data points as much as possible. This lower dimensional data is easier to visualize and analyze. This is our goal: simplified yet informative data. I'll construct a graph where each data point is a node and I'll connect each point to its k nearest neighbors. K is a parameter I need to specify beforehand. This creates a neighborhood graph, representing local relationships between data points. This step is crucial for capturing local neighborhood information. KNN stands for k nearest neighbors. Isomap isn't a linear method like principal component analysis, PCA. Instead, it tackles dimensionality reduction by finding relationships in the data that aren't just straight lines. Think of it like this: imagine trying to describe a curvy road using only straight lines. You'd miss a lot of detail. Isomap, on the other hand, captures the curves. Isomap's superpower is keeping the distances between far-apart points accurate, even if it messes up the distances between closer points a little bit. It's like drawing a map, where the overall shape of the continents is spot on, but a small island might be slightly misplaced. It prioritizes the big picture. How long Isomap takes to run depends a lot on how much data you feed it. While technically the complexity is cubic, meaning runtime goes up by the cube of the data points, in practice, many optimizations make it behave almost like a quadratic equation, runtime increasing by the square of the data points. This means, doubling the data doesn't double the time, it quadruples it. But that's still an awful lot of extra time. To work its magic, Isomap needs to know which points are close to each other. It does this by using a parameter called k nearest neighbors, KNN. KNN is a value, let's say 5. Isomap will look at each point and only connect it to its 5 closest neighbors. This creates a neighborhood graph, a visual representation of connections, helping Isomap calculate the curvy paths, geodesics, between distant points, forming the basis for its nonlinear dimensionality reduction. Isomap is a technique used to simplify complex datasets, bringing down the number of dimensions without losing too much information. It's like taking a 3D object and representing it effectively in 2D. It's really useful for simplifying high-dimensional data which is difficult to visualize. This quiz tests your understanding of Isomap, a technique used to reduce the dimensions of your data. Let's see how well you know it. We'll look at several statements about Isomap and determine if they are true or false. Get ready to test your knowledge. Remember, there might be more than one correct answer. This means you need to carefully assess each statement. Think about it. Isomap isn't linear. It handles complex, nonlinear relationships in the data. It's important to remember that a linear approach assumes a straightforward relationship between variables, while Isomap can navigate more intricate data patterns. I see this as about global distances. Isomap does an excellent job of preserving the relationships between points that are far apart. That's what makes it powerful for certain types of data analysis. Here, we're talking about a crucial parameter. To use Isomap, I need to define how neighbors are determined. This parameter, the number of neighbors or a radius, tells the algorithm which points are considered nearby, shaping its understanding of the data's structure. Okay, now you're ready to submit your answers. I'm confident you've mastered the key ideas of Isomap, so good luck. Isomap's superpower is preserving the big picture. It focuses on keeping the distances between far-apart data points accurate, even if it means some small, local distances might be a little off. Think of it like a map. Isomap prioritizes getting the overall shape of the country correct, even if some local roads might be slightly misrepresented. You need to tell Isomap how to find its friends. To build its network of connections, Isomap needs to know how many data points to consider nearby for each point. You need to specify this using a parameter. That's similar to deciding how close two people need to be before considering them friends on social media. Isomap's runtime grows fast with lots of data. The time it takes Isomap to run increases quickly as you add more data points. The relationship isn't perfectly quadratic, it's closer to cubic, but for this question, it's a reasonable approximation. Think of it like baking a cake. The time it takes to bake increases as you add more ingredients. Isomap is not linear. Isomap actually uses a nonlinear approach to reduce the dimensionality of data. It doesn't just use straight lines to project data onto a lower dimension, instead it uses complex, curved pathways. That makes it different from techniques like PCA, which are linear. This is the core question of the quiz, asking you to assess your understanding of Isomap's properties. This instruction highlights that multiple answers can be correct and prompts you to analyze each option carefully.